Welcome everyone. We are delving into a fascinating data structure called a tree, which combines features of a binary search tree, BST, and a heap. We will explore its purpose, construction, and performance, as well as provide some explanations and examples. First, let's take a look at binary search tree. Binary trees are excellent for storing and retrieving data. In a binary search tree, each node has at most two children, a left child and a right child. The key property of a BST is that for any given node, all values in its left subtree are less than the node's value, and all values in its right subtree are greater. For example, consider the following binary search tree. In this BST, the left subtree of the node with a value of 10 contains values less than 10, and the right subtree contains values greater than 10. This definition applies to all nodes in the tree. For example, the right child of 15 is 20, which is greater than 15, and the left child of 15 is 12, which is less than 15. A perfectly balanced binary tree, also known as a complete binary tree, is a tree in which all levels are fully filled, except possibly for the last level, which is filled from left to right. This structure ensures the tree maintains balance, optimizing search operations. The height of a balanced binary search tree is logarithmic in relation to the number of nodes, resulting in a time complexity of big O of log n for operations such as insertion, deletion, and search, where n is the number of nodes in that tree. Conversely, a perfectly unbalanced binary tree is a tree in which every parent node has only one child, typically resulting in a linked list-like structure. These trees offer poor performance for search operations due to their linear nature. Now let's compare the performance in perfectly balanced and perfectly unbalanced binary trees using big O notation. We can see that the perfectly balanced binary trees are much more efficient than the unbalanced trees. Now, let's introduce heap data structure. A max heap is a specialized tree-based data structure where each node is less than to its parent. For example, consider the following max heap. In this max heap, every parent node is greater than or equal to its child nodes. Now let's talk about trees, which combine the properties of both BSTs and heaps. A tree is constructed like a binary search tree, where each node has a priority assigned to it, typically generated randomly. So we use the elements that we want to store as keys and maintain the BST properties, and assigned randomly generated properties and maintain the heap properties for the priorities. This is the constructor of a tree. It initializes a random priority for each key. Let's take this example. Consider inserting 1, 2, 3, 4, 5. Tree.insert 1. The insertion will be recursively. Here, the base case will be executed because the root is null. The priority generated is 36. When tree.insert of 2 is executed, the element 2 will be inserted to the right of 1 with a random priority of 79. Although the binary search tree property is satisfied with 79 being greater than 36, the heap property is not met with the right priority is greater than the parent priority, necessitating a left rotation to maintain the heap priority without affecting the BST properties. An AVL rotation is employed. By definition, AVL rotation doesn't mess with the BST properties, so the right of node 1 will be the left of node 2, which is null, and the left of node 2 will be the node 1. Now both BST and heap properties are satisfied. Now insert 3. 3 is greater than 2, so it goes to the right with a randomly generated priority 40. The heap property is valid since 40 is less than 97. Now let's insert 4. We go right then right. 4 would be the right child of 3 with a priority of 93. This violates the heap property, so the algorithm will do left rotation, so the resulting tree, the new node, still has higher priority than its parent, so another left rotation. Now the algorithm maintained the heap properties. Now insert 5. The priority generated is 59. It will be inserted to the right. The heap property is maintained, so it is done. Now let's insert 6. The priority generated is 2. The heap property is maintained, so we are done. We got a pretty balanced tree. In average, the time complexity is big O of log n, but it still has a big O of n worst case, because the worst possible scenario we could have priorities 6, 5, 4, 3, 2, 1. Aragon and Seidel in their randomized search tree paper showed that there is no hard guarantee that the tree will be balanced. The probability of the height h of a tree with n nodes being greater than the natural logarithm of n by a factor of some constant c is bounded by this formula. For a tree with 10,000 nodes, the probability that the height of the tree is greater than 100 is 1 over 2.5 billion.
So you're telling me there's a chance?
In summary, trees offer a balanced combination of binary search trees and heaps, maintaining both key ordering and priority-based properties, while typically providing efficient average case performance with a time complexity of big O of log n. They may occasionally exhibit worst-case behavior, big O of n, though such occurrences are rare. Trees remain versatile and efficient data structures suitable for various applications such as scheduling, network routing, and cache management. By understanding their construction and properties, developers can effectively utilize trees to enhance system efficiency and scalability.